In the last video, we talked about the identity matrix I, and we briefly mentioned the concept of an inverse matrix. We're going to look at an inverse 2 by 2 matrix, 2 rows, 2 columns, and show how we solve for it and what uses it might have. We're going to bring back the concept of the identity matrix, and then once we learn how to solve it for a 2 by 2 in future videos, we can learn how to solve it for larger matrices and think about what the actual application and the power of an inverse matrix is. In reality, you'll do this inverting it by hand only a few times. Most of the time you use your computer to do it, but it's important to understand the concept of what the inverse matrix is actually doing. All right, so let's say I think this is the same matrix I showed in the last video, but just an arbitrary matrix, a 2 by 2 matrix, 2 columns and 2 rows. And we can also name it in a generic sense with A, B, C, and D. And from the last video, when we introduced the identity matrix I, remember I is it could be any size, right? But it's always a square matrix. If it's a 2 by 2 matrix, it looks like this, 1, 0, 0, 1. And the rule of the identity matrix is it has ones across the diagonal and zeros everywhere else. And the importance of the identity matrix, remember, is you multiply the identity matrix with any vector or matrix, and you get the original vector or matrix back again. And the other definition of the identity matrix is if you multiply a matrix by its inverse, right, which we dictate by this power -1, then we get the identity matrix. And you can revert it too, right? So there could be inverse matrix multiplied by matrix A, and you also get the identity matrix. So we know our matrix A, 5, 3, 4, 2, that's given to us. How do we determine this inverse matrix defined here? So for a 2 by 2 matrix, there's a simple rule, and then we'll define it generically, and then we'll solve for this specific example problem. Before we can do this, we need to reintroduce the concept of the determinant. We briefly introduced the concept of the determinant when we were looking at cross products. In that case, we looked at a 3 by 3 determinant using the two vectors as two of the rows, and the top row was your basis vector, I hat, j hat, k hat terms. In this case, we're going to just look at the determinant of your original matrix A. So real quick, you write your matrix terms, and then instead of the square brackets, you use these straight vertical lines to represent that you're solving for the determinant, okay? And you're doing the difference of the cross products. So you always start with the top left, and you go 5 times 2 minus 3 times 4. And you will find a scalar as your determinant for this 2 by 2 matrix, right? So this determinant is then used to help you solve for the inverse of this matrix. So the definition, the generic definition, is shown here. So if my matrix is defined as A, B, C, D, the inverse of this matrix is 1 over the determinant, 1 over -2, that's what I have here, times the matrix that's the original matrix rearranged in this very specific way, right? So A and D swap places, right? These left, the left diagonal is swapped. And then the other cross diagonal, the signs change. So B changes to -B, C changes to -C. Don't worry about why this is the rule. Just know that this is, and we apply it, okay? So if I look at our specific example here, I would have 1 over my determinant, which is -2, so 1 over -2, times I swap my left diagonals, so 5 and 2 swap, so I have 2 and 5, and then the signs for the other diagonal are changed. So +3 here, so -3 here, +4 here, so -4 here. And then I multiply this scalar now to this matrix. And if you remember from a previous video, we just multiply this to each individual term. So negative 1/2 times 2 is negative 1. Negative 1/2 times negative 3 gives me positive 1/2. Negative 1/2 times negative 4 gives me positive 2. And negative 1/2 times 5 gives me negative 2.5. Right? And that's how I get my inverse A matrix. We could do the reverse to make sure that it works in the same way, right? So I could take the determinant, right? So just take these same 2 steps, but now instead of taking it for the matrix A, we'll take it for the inverse matrix. So, because the inverse of the inverse should be the original matrix. That's the idea here. So if I take the determinant here, this is my matrix right here. So I'll do negative 1 times negative 2.5. That's right there. And then 2 times 1.5 right there. So you subtract those two. It's always top left product minus the top right cross product. Then you get positive 2.5 and minus 3, so you get negative 1.5 as my determinant. And then we apply this rule now. So now inverse of the inverse gives me the original matrix A, or should give me the original matrix A. So 1 over negative 1.5 is negative 2. And then we apply the same rules as we did before, right? So I'll swap these two. So negative 2.5, negative 1, and then change the signs of these. So negative 1.5, negative 2. Then negative 2 multiplied by this matrix gives me positive 5. Negative 2 times 1.5 gives me positive 3. Negative 2 times negative 2 gives me positive 4. And negative 2 times negative 1 gives me positive 2, which is my original matrix A. All right, so these are the rules that we're going to apply. And I'm going to show you an example of when we can apply it. So the rules about the identity matrix being the product of a matrix and its inverse can actually be used to help solve a problem that we're actually interested in. So a common use of matrices is to consolidate equations. And I think I've shown you this in a previous video. But let's say this matrix A, that is the same one that we used earlier, is the coefficients for this set of equations. So I have 5, 3, 4, and 2. And remember, this is just a reference to help us remember the rule. Now, how can I write this equation in a matrix form? Understanding how to write an equation with unknowns in a matrix form allows us to utilize this property. So the way I can rewrite it is in this form right here. The matrix A, which contains the coefficients in front of my unknown variables x and y, multiplied by, I use capital X to represent the vector that contains x and y here, right? The vector of my unknowns is equal to, I call this my B vector or B matrix, which are all the constants, right? So if we look at it from this perspective here, this A matrix contains all my coefficients here. This X vector contains x and y, and this B vector contains my constants 4 and 6. So first, convince yourself that this is the same as this component right here, right? So remember how we multiply a matrix to another matrix, or a matrix to a vector, right? You take the row of the first and you multiply it by the column, or take the dot product of the first of the row and the column vector, and that dot product will give you the value right there. So it'll be 5 times x plus 3 times y is equal to 4. If you take the second row, you would fill and combine with the second row of the B vector, right? So 4 times x plus 2 times y is equal to 6. So this has a direct relationship with this set of equations. Okay, so understanding that, if we look at it from the generic perspective as A times x is equal to B, this is when we can apply the concept of inverse matrix. So if I multiply the inverse matrix over here and multiply it over here as well, then I'm not changing the equation, right? This is the same thing as multiplying by 2 on one side, multiplying 2 on the other side, right? So you're being consistent. So that's what this is right here. So we multiply the inverse matrix A over here. Now it's important whether you put on one side or the left side or the right side. That makes a difference. So you have to be consistent. Well, inverse matrix multiplied by the matrix or a matrix multiplied by inverse matrix both give you the identity matrix, right? So the product of these two give me my identity matrix. The identity matrix multiplied by any matrix gives me the original matrix, right? So the identity matrix times x just gives me my vector x. So that drops out. So now x is what I'm trying to solve for. So if I know my inverse matrix, then I could just multiply that by my b constant vector, and I automatically solve for both unknowns at the same time. This is the power of it, right? For a 2 by 2 matrix, this might not be as meaningful, but imagine that you have a 100 by 100 matrix. You don't want to solve that by hand. That'd be very difficult too. But if you're able to solve for the inverse of the matrix, or get a computer to do that for you, then you can solve for all your unknowns all at the same time, right? So that's, I do that with my students in my class for heat transfer, and you can use it for a lot of different other types of problems and solve many equations simultaneously. So for our specific case, because we know what the inverse matrix was, right? This was from the previous problem. I take that inverse matrix, multiply by my constant vector b, 4 and 6, and then what do we get? We get -1 times 4, -4. 1.5 times 6, 9. And I get 2 times 4, 8. -2.5 times 6, 15. And simplify this, right? So you get 5 and -7. So this is saying that x is equal to 5 and y equals -7 satisfies these two. So we can check it. All you have to do is plug it back into both of these equations and double check, right? So plug in 5 for x and -7 for y, and you solve out the problem, and you do get your 4 and 6. So this could be a larger problem. Solving for the inverse of the matrix would be, we would utilize different methods in those cases, but that's the general concept. Now, this does not always work, and I'll explain a type of matrix when this does not work. When we have a matrix A that we cannot solve for the inverse of a matrix, we call this a singular matrix. This happens when this is undefined, the 1 over the determinant, right? So when the determinant is equal to 0, then we call this matrix A a singular matrix. And in that case, you cannot solve for inverse of the matrix. Now, when might this happen? Well, we know that we can solve the determinant of a matrix by the cross product here minus this product here. So when A times D minus B times C is equal to 0, then we have a singular matrix, and we can't solve with the method that we solved before, right? And there is no inverse. If the determinant is equal to 0, then this is equal to 0. Then I know that AD is equal to BC. We can see that the ratio of A and B and C and D are the same. The way I like to think about it is if I say C, right? So let's say that A and B are like set values, and I want to know what values C and D would have to be for this to be a singular matrix. So if I isolate C, C is equal to A times D over B. But this is also true, right? D over B is equal to D over B, or D is equal to B times D over B, right? This is just saying that D is equal to D. So why am I writing it like this? Well, if this is both D over B, this is basically saying if I have a row 1 already defined, and my row 2 is just a factor or a scaled version of A and B, then I know I have a singular matrix. So what do I mean? I mean, if I have 2 and 5 and I just multiply the top row by 2 and I get 4 and 10, then I have a singular matrix. If I have 12 and 3 and divide everything by 3, then I get 4 and 1, then I have a singular matrix. And we showed it here, right? You can determine A is equal to 0. So, but why on a practical level would that be? Well, if I just look at this example here, remember from the previous slide, we said that we can use a matrix to help us define a set of equations. Well, when you have two unknowns, you need two distinct equations to help you solve for these unknowns, right? So let's say E is some arbitrary constant, right? And let's say this top row helps me define an equation 2x plus 5y is equal to some E. My second equation's got to be something different. But if it's just multiplied by 2, if I multiply this by 2 and I get 4x plus 10y equals 2e, this does not give me any more information, right? So I would not be able to solve for x and y from this because I basically only have one equation and I have two unknowns. So if you solve for your determinant and you find that you have a singular matrix, you need to go back and make sure that your matrix or your problem statement is well defined because a singular matrix tells you that your problem is not well defined. All right, so next I'm going to show you a set of example equations. I want you to hit pause and try to solve it on your own, and I'll give you the solution, and you can check it on your own as well. Take a look at these 4 sets of equations and see if you can solve for x and y with the method that we showed earlier. Right, so hit pause. First step, remember, you convert the pair of equations into a matrix A multiplied by an unknown vector x, which has x and y, equal to a vector B that has your constants, right? So convert that first, and then figure out how you're going to then solve for the inverse of the matrix A and see how you would utilize that to solve for x and y simultaneously, right? Some of these problems are not clean. The numbers are going to be messy. I would recommend keeping them in fraction form until the very end. That's the way I did it. So hit pause, try to solve them on your own. If you're struggling, I may recommend you solve number 4 first. That is a little bit cleaner numbers. But try it out, and then when you feel like you've made a good attempt or you feel comfortable, if you don't, rewind back to the section where I go through the example and make sure that you understand those steps. And then once you feel ready, then play out the rest of this video, and I'll show you the solutions. I'm not going to walk you through the solutions. You can press pause after I show you the solutions and you can check your work. All right. So hopefully you've tried the problem. I'm going to show you the solutions now. I'm not going to walk you through the process. It's the exact same thing, right? We set up the matrix A, vector B. We solve for the determinant. We use the determinant and this method to solve for the inverse matrix A. And then we use inverse matrix A multiplied by the vector B to solve for the x and y unknowns simultaneously. So the next set of videos will look at larger matrices that make more sense to solve in this way, right? In an actual case like this, you would probably just solve for x and y individually with your algebra, your knowledge of algebra. But when the problems are much larger, it becomes much more difficult. But that's when you can utilize computers and other methods to solve for your inverse matrices. And once you solve for the vector, right, automatically the top row would be your x value, the bottom row would be your y value. Okay, so hopefully that made sense. If you have any questions, feel free to put it in the comments, and then we'll look at larger scale problems in the future videos.